Hello, everyone. Mr. Martella back here with the final part of our discussion on plate tectonics, continental drift, Alfred Wegener, Pangea, all of those things. So, welcome back, and we're going to pick up right where we left off in the last video. And at this point, we are talking about how scientists now had proof that the tectonic plates moved. But if you think about it, how far have we really come? Wegener, Alfred Wegener, the German climatologist that was working in the late 1800s, he had proof that the tectonic plates moved also. But remember, by the time it was all said and done, Wegener's big problem was he couldn't prove how they moved. He couldn't find the mechanism that actually made the tectonic plates move across the face of the planet. All right. So remember, he had fossil evidence, he had geologic evidence, and he had climate evidence that proved that the continents moved. Scientists in the early 1900s came along and they had a bunch of evidence from the seafloor that proved that these plates moved. So they had discovered the the mid-ocean ridges using sonar. Remember the vast underwater mountain ranges? They had also discovered that the age of the rock on the sea floor around these mid-ocean ridges had a pattern. They discovered that the rock closest to the ridge was younger, and as you moved away from the ridge, it got progressively older. Okay? So they came up with this idea of the spreading center and that the sea floor was spreading, that new crust was being created on this planet. But the question was, if new crust was being created, how come the Earth wasn't getting any bigger, right? So the scientists also found mid-ocean ridges, and then opposite of these, almost parallel to them in every ocean, they found the deep ocean trench, which are some of the deepest points in the ocean. And this is where the Earth is pulling the old crust back into the asthenosphere and essentially recycling it into new land. So new land is created in the spreading centers at the mid-ocean ridges. Old land is being destroyed at the deep ocean trench. And remember, the deepest point in any ocean that we've ever discovered at this point is Challenger Deep at the Mariana Trench. It's so deep that you could actually take all of Mount Everest, stick it down in that canyon, and the top of the mountain still would not poke out of the surface of the water. Okay? So the Marianas Trench, extremely deep, all right, as well as many of these ocean trenches. So that's a little bit of review. That's how we got to where we are today. And once again, we are at a point where scientists now had proof that tectonic plates moved. But the same question remained. How could these plates move thousands of miles around the planet? And we teased this at the end of the last video. The answer was, and still is, in the asthenosphere. So, what do we know about the causes of plate movement? Well, we know that tectonic plates are part of the lithosphere, which sits atop the asthenosphere a layer of hotter, softer rock, all right? Rock in this layer, we know, moves by the process of convection. And you've seen convection if you've ever seen a lava lamp in action, all right? The material heats from the light at the bottom of the lava lamp. It rises until it gets far enough from its heat source that it can cool, and then it sinks again before it's heated and rises. and you get what we call these convection currents that are constantly moving the material in the lava lamp up and down and up and down. So that's what I just described to you. If this sinking and rising motion continues, you have an official, what we call convection current. And now you have a motion that transfers heat energy throughout a material. So if we take a look at this image here, I'm going to have to, let me reset it in the presentation really quickly here, guys. Because we want to be able to see the movement here in this image. So let me just quickly reset it. And let's get back to what we were doing here. All right, so you see here, this is demonstrating convection, okay? You've got the cool material sinking. You see the blues over here coming down and sinking, all right? And then the material heats, it moves, and it's going to then rise again, all right? As you see, it gets here. So we get these convection currents moving the material. So anything that is up here is going to ride right along the top of the currents, okay? So convection currents in the mantle are slow, all right? The tectonic plates are moving only a couple of inches per year. If there were humans around as India began to collide with Asia, there's no way that you would have been, or that anybody could have been, standing along the southern coast of Asia and screamed, "Oh, here comes India! Everybody!" No, these continents are not moving that quickly. They're not moving that fast. Okay, they only move a couple of inches per year. They move about the same rate that your fingernails grow. Okay, so these continents drift. That's why it's taken 200 million years to get to Pangea, to where we are today. And that's why it's going to be another 200 million years before the next supercontinent forms on this planet. So the tectonic plates in the lithosphere are carried on the asthenosphere like big, heavy boxes moving on large rollers. What we're going to find out here is that if there's the continental crust that's part of, let's say, the African plate, is never going to end up on the South American plate, okay? So the continents and the crust can only travel as far as the borders of their plates, okay? So if we think of, the beginning and the ends of these rulers as the tectonic plates, and then these boxes as the crust that is being carried, this box is not going to jump on its own from this ruler to this roller, okay? So that's the same as the tectonic plates. This box isn't going to end up over here. They're going to move, but they're going to stay on their own rollers. So once again, the continents are going to move, but they are going to stay within the boundaries of their plate, okay? Over millions of years, this results then in the plates being carried thousands and thousands of miles. So, scientists suspect that there are two final motions here that help, all right? Slab pull and ridge push. These extra forces help to move the plates. Try and think of it this way. If you've ever seen a train, a choo-choo train, some of those trains are so long that they don't just have engines in the front. All right, engines in the front would not be enough to pull the entire load. So you also see engines in the back. All right, so you have the engines in the front that are providing a pull, and you have the engines in the back that are providing a push to help move these systems of cars along their tracks. So slab pull, ridge push, along with convection currents are the forces that are moving these tectonic plates over the surface of the Earth. Slab pull occurs where gravity pulls the edge of a cool, dense plate into the asthenosphere. So slab pull is a feature that's happening in the deep ocean trenches. All right, slab pull, that's where the edge of the cool, dense plate is being pulled back into the Earth. Once again, this happens at the deep ocean trench. Now, ridge push, on the other hand, happens where it says it happens, okay? So it occurs when material from a mid-ocean ridge slides downhill from the ridge and pushes the rest of the plate apart, okay? So at the spreading centers, at the mid-ocean ridges, you're getting the ridge push. Then, all the way on the other side, where the crust is being destroyed, you're getting the slab pull, which is essentially gravity. Make sense? All right, here's an image then that shows you, I don't know why my image went away, but there it is again. It shows you, here is the deep ocean trench. All right, so this is the area where slab pull is pulling the old, dense, heavy plate back into the Earth. And then here at the mid-ocean ridge is where you are getting your ridge push. All right, where the magma pushes up, it cools, and it gives a push at the spreading center. All right. So let's kind of try to put this entire theory now together. Since we understand the actual mechanisms in the asthenosphere that are moving these plates, we now have a theory that states that the Earth's lithosphere is made up of huge plates that move over the surface of the Earth. One plate cannot shift without affecting the other ones nearby. And plates generally have three motions, all right? At their boundaries, they're either moving apart, they're pushing together, or they're scraping past each other, all right? Like this, scraping past each other, okay? And over the next few lessons, we are going to take a look at what we call divergent boundaries, convergent boundaries, and transform boundaries. Those are all called different things because there are different plate motions at those boundaries. We'll find that most major earthquakes, volcanic eruptions, and mountain ranges appear at tectonic plate boundaries. These are geological hotspots, okay? So if you take a look here, one final image for you. These are the major and some minor tectonic plates of the planet. The red arrows here indicate whether that boundary is, whether the plates are pushing together, like they are here at the Aleutian Trench, where the Pacific plate is being pulled underneath the North American plate. Here, you see one of those transform boundaries, where the Pacific plate and the North American plate are sliding past each other. The North American plate is moving to the southeast as we see the Pacific plate moving to the northwest. By the way, this is a very famous fault line on this planet called the San Andreas Fault, and we're going to study that as we get to earthquakes. Okay? So here you see a divergent boundary, an area where the plates are actually moving apart. Okay? So if you look at the major tectonic plates, we have the Eurasian plate, the North American plate, the African plate, the Indian plate, the South American plate, the Pacific plate, and the Australian plate. Finally, the Antarctic plate. Those are the major ones. You also see some minor plates within here: the Caribbean, the Nazca, the Cocos, the Juan de Fuca plate, the Filipino plate. All right. Remember, I'd like you to think back to that hard-boiled eggshell as you're looking at this image. Okay. And think about how, although the eggshell is broken, it still offers a sort of outer layer, a crust, just like you see here with the lithosphere and the tectonic plates. All right, I hope you guys learned something today. Our next video will be about divergent boundaries, and we'll see you then.